Thermal mass is another method to reduce energy transfer in buildings. It consists on the use of materials of large thermal heat capacities called heat sink. In this case, when temperature outside of the building is relatively high, the thermal mass will absorb energy in order to avoid overheating of the space, while this heat will be released when the temperature inside the space will drop. Therefore, the resulting temperature change in the building will be reduced as can be shown in the figure. This ensures thermal comfort in the inner space. For example, in the following figure, we can see the profile here. So we have first the profile of the external temperature, which represents the variation of the external temperature for a whole day. We have the variation of internal temperature for the case of a building with low thermal mass, and we have the variation of temperature for the case of a building with large thermal mass. So what is happening is that for the case of a building with a low thermal mass, the variation of temperature will closely follow the temperature profile of the external temperature. And in this case, the inner space is not totally in the comfortable zone because we have temperature above the upper comfort temperature and temperatures below the low comfort temperature. While on the other hand, when we use large thermal mass, we can see that all temperatures during the whole day are between the low comfort temperature and the upper comfort temperature, maintaining a comfortable effect during the whole day. So we can say that in this case, the presence of large thermal mass will delay the building response to heat sources and therefore will cause a thermal lag effect. Due to the positive role played by the thermal mass, which will absorb heat during the day, avoiding overheating, and releasing heat during the night to warm the inner space. The presence of thermal mass is particularly important in case of high temperature difference between day and night, where the thermal mass will store heat during the day and release it back during the night. In the following figure, we can compare the cases of heavy mass buildings in top figures and light mass buildings in lower figures. We can see that in the case of heavy mass building, during the day, heat is absorbed by the thermal mass, avoiding overheating of the space, and as you can see here, this will maintain an acceptable temperature. On the other hand, in case of light mass building, during the day, the thermal mass will be saturated at a certain stage and will not be capable anymore to absorb heat, which will lead to overheating of the space and reaching warm temperature. On the other hand, during night, if we take the case of heavy mass building, once the outer temperature becomes low and the inner space temperature drops, the thermal mass will release back the heat in order to maintain a comfortable temperature. And then we can conclude that during the day and the night, we can ensure a comfortable temperature in the space. On the other hand, for the case of light mass building, what will happen during the night is that the thermal mass will release the amount of heat, but it will not be enough to warm the space for the whole night. So once all heat is released back and no more heat is present in the light mass building, then the inner temperature will drop below the comfort level, and this will induce thermal discomfort. In the following figure, for example, we can see how the presence of thermal mass can reduce the need for the operation of a heating ventilation system. For example, here we can see that from 10 a.m. to 5 p.m., the thermal mass will play the role of absorbing energy to avoid overheating of the space. In the second stage, from 5 p.m. to 11 p.m., the inner temperature will begin to drop. This is why there will be a high heat rate of release from the thermal mass building towards the inner space to warm it. From 11 p.m. to 6:30 a.m., already a large quantity of heat is already supplied. This is why the rate of heat transfer will be reduced, and this will allow to maintain an acceptable temperature for these hours. But after 6:30 a.m., between 6:30 and 10 a.m., nearly there is no more heat in the thermal mass to be released. This is why we should operate the heating ventilation system. So we can see that it will depend on the heat capacity of the thermal mass will affect a lot the number of hours needed for operation of the heating ventilation. And heavier is the mass, is the thermal mass, lower will be the number of hours needed for operation of the ventilation system, and therefore higher will be the energy savings. This is chapter 2. We are done with the course material, and now we will start with examples on this chapter. We'll start first by a problem on sensible and latent heat. The question is, how much energy is needed to raise the temperature of 38 grams of ice at minus 20 degrees to water vapor at 120 degrees? The specific heat of ice is 2.09 joule per gram per degree. The specific heat of water is 4.184 joule per gram per degree, and the specific heat of steam is 1.89 joule per gram per degree. The melting heat is 334 joule per kilogram, and the evaporation heat is 2260 joule per kilogram. So in this example, what we can see is that we want to transfer ice to vapor. So we will pass first from the ice phase to ice plus liquid. So we have a phase where we have two change of phase from ice to liquid. Then we have a certain phase with this liquid, with the liquid heating. And after this, when we reach the evaporation temperature, we will have change of phase from water to vapor. And after this, we will be having heating of vapor from 100 degrees, which is the evaporation temperature, to 120 degrees. So we should pass by different phases in order to go from the ice state to the vapor state. So we should first divide our calculation, find the amount of heat needed for each phase, and at the end we will sum all these amounts to get the total amount of heat that should be supplied to our system to go from the initial to the final state. So what we will do is we will see that we should divide the different steps and calculate for each step what is the amount of heat needed. So first, as we said, the initial state is ice. Okay? So first we have a certain state with solid. We have a solid that is heated. And the starting temperature is minus 20 degrees until we reach the melting temperature. Between these two temperatures, we have the solid state. So in this case, this is a sensible heat. Okay? Because when you don't have change of phase and you supply heat, temperature will increase, and this is called sensible heating. So sensible heating for the solid is the mass of the solid times the capacity, the heat capacity of ice, times the variation of temperature delta T. First, we should pay a lot of attention for units. The specific heat in this problem is given in joule per gram per degree. So in order to obtain Q in joule, I should use a mass in gram because the specific heat is joule per gram. And since also it's per degree, delta T should be in degrees. Okay. Now, delta T in degrees is the same as delta T in Kelvin, because you know what is the relation between Kelvin and degrees? You have the temperature in Kelvin is equal to the temperature in degrees plus 273. Okay, so since here it's a linear relation, so when you do delta T in Kelvin or delta T in degrees, since the difference between them is a constant, you have same delta T. Okay, so now in this way we can calculate first the heat needed to raise 38 grams of ice from minus 10 degrees to 0 degrees. Now, once we reach 0 degrees temperature, we know that the melting temperature of ice is 0 degrees at normal conditions. So what will take place now is a change of phase. So in step 2, we'll have a change of phase. And in this case, the type of heat is called latent. So we have latent heating. Okay, and the amount of latent heat is calculated, as we have seen in the course material, by m times the latent heat of melting, which is given in the problem to be 334 joule per gram. So all we need to do to find the amount of heat provided is to multiply the latent heat per unit mass by the mass to melt, which is 38 grams. In this way, we find that the melting heat is 12,692 joules. Now, once this phase is done, then we move to the heating of the liquid. So now we have 100% liquid in the third step. So here in step 1, we had 100% solid. In step 2, we have change of phase, so it's mixture of solid and liquid. In step 3, we have 100% liquid. So now, also, since we have one phase and we are supplying heat, so the form of heat is sensible. So it's sensible heat, which will lead to variation of temperature. But for change of phase, for a pure material, it will take place at constant temperature. So here melting will take place at 0 degrees. After complete change from solid to liquid state, the temperature will increase again. So it will go now from 0, which is the melting temperature, to 100 degrees, which is the evaporation temperature of water. So now the amount of heat that should be supplied is also given by the same formula for sensible heat of mc delta T. But what is different from the first step is that now we take what? We take the specific heat of water, while here we considered the specific heat of ice. And as you can see here, the specific heat of water is higher than the specific heat of ice. And of course, paying attention for the units, we put the mass in grams and the temperature in degrees. So delta T is 100 minus 0 is 100, which will lead to Q equal to 15,899.2 joules. Now, once we reach 100 degrees, which is the evaporation temperature, we should now have change of phase, because we will go from the liquid state to the vapor state. So here in step 4, we have a change of phase. And in this case, we go from liquid to vapor. And therefore, to calculate the amount of heat provided, this is latent heat type. So it's m times the latent heat of evaporation, which is also given in the problem. So all we have to do is to multiply the latent heat of evaporation per unit mass by the mass here, which is 38 grams, we obtain the amount of latent heat to go from liquid to vapor, which is 85,880 joules. Finally, once 100, we have 100% of vapor, so the change of phase is done. We can go to the final step, which will raise the temperature of steam from 100 degrees to 120 degrees. So also here, since we have one phase, it's a sensible heat, and it's calculated by M times C times delta T. But now, of course, the specific heat is the one for steam, which is also given. So we multiply 38, which is the mass here in gram, by 1.89 joule per gram per degrees, by delta T, which is 120 degrees minus 100 degrees. We get the amount of heat needed to raise the temperature of steam from 100 to 120 degrees. And at the end, to find the total amount of heat that should be provided to achieve this operation, we should add all numbers found in the 5 steps. So by adding them, we get the total amount needed to heat the required mass from minus 20 degrees to 120 degrees.